All right, this is the second part of section 10.2. We're still comparing two means. We're going to get more specific today on how to do your 4 steps for confidence intervals. So we've broken again section 10.2 into sort of 3 sets of notes. Today's 10.2.2, we're going to construct and interpret confidence intervals for the difference in two means. So we're going to try to estimate the difference in two means from two different populations. And again, we're going to use our 4 steps. All right, so a couple of details before we get to our 4-step process. The confidence interval, the formula for the confidence interval for the difference in two mu's is going to be the difference in the statistic, so x bar sub 1 minus x bar sub 2. So that together is the point estimate. And then plus or minus the critical t value, and then the standard error, the square root of, and then that is the variance from each of our sample statistics or sample data. So remember too that because we did that S substitution in there, we're using a T distribution, not Z, not the standard normal distribution, but a T distribution. All right, so T star, again, is going to be that critical value. If we're going to do it with a T table, we need to know how many degrees of freedom in order to find that critical T value. So we're going to really suggest that you do this in the calculator, use technology, not just to find, not to find your T star, but to do the whole test, right? To run the confidence interval, just use your calculator. It's going to be so much easier. The formula here for this confidence interval is getting more and more complicated, more and more accident prone when you do these calculations. So just use your technology, right? So in order to get your degrees of freedom, you would just do the whole test in your calculator, and then when it gives you your confidence interval, it will also tell you the degrees of freedom, and then you would record that down on your piece of paper. The other option would be to use the smaller of either n sub 1 minus 1 or n sub 2 minus 1. So 1 minus the sample size, whichever is smaller. Okay, so one note to your calculator, when you do these tests in your calculator, it's going to ask you if you want to pool your data. Right, so first you're going to do stat, test, and you're going to do a 2-sample T int. That is what the Texas Instrument people call this test in your calculator. So 2-sample T interval. It will ask you at some point if you want to pool your data, and your answer will always be no. Your calculator is smart enough to know when it's supposed to run a pooled test, and that pooled test is really only when we have a difference in proportions, like we saw in section 10.1. In section 10.2, when we do means, we do not pool the data. So if you remember when we were doing pooled data in 10.1, the calculator does not ask you if you want to pool it. It just does it automatically because it knows when you're doing difference in proportions. It knows what test to pull the data in, and that's the hypothesis test when you're doing differences in proportions. When you're doing differences in means, you don't generally pool, and so when they ask you, do you want to pool the data, you will always say no. Your calculator knows to do it when it's supposed to be done, and when it asks you if you want to do it, you always say no. All right, so the conditions we need to check. We're going to check random. Again, we need to make sure that we're talking about two independent random samples from two different populations, and then that or a randomized experiment with two treatment groups. All right, again, we have to check that we didn't sample more than 10% of either of the two populations. And then we talked about this in the last video. 3 situations, right? The population distributions are normal, so therefore the sampling distribution of the difference in the X bars is going to be normal. The sample sizes are both over 30. So we know the central limit theorem tells us that each of the individual sampling distributions is normal, so therefore the difference is as well. And then if they're less than 30, the sample sizes, then we need to graph each of the sets of sample data in, I would suggest, 2 box plots and check for outliers or strong skewness in those 2 box plots. Okay, so let's look at an example for 2 different means. So this is going to be a confidence interval using our 4-step process. Okay. So Ashton and Olivia want to know if generic chocolate chip cookies have as many chocolate chips as name brand cookies on average. All right, so to investigate, they randomly select 10 bags of Chips Ahoy cookies and 10 bags of Good Value cookies and randomly select 1 cookie from each bag. Then they carefully broke apart each cookie and counted the number of chocolate chips in each. All right, here are the results. So we have 2 sets of data, right? We have sampled a bunch of Chips Ahoy cookies and we've sampled a bunch of Great Value cookies. Each of these numbers is the number of chocolate chips in each of the 10 cookies. All right, so probably the first thing we want to do is put that data into a list, right? Or into 2 lists. So let's say Chips Ahoy goes in list 1 and Great Value goes in list 2. Why don't you pause this video and put that data into your calculators, and then we'll resume. All right, so part A is asking us to construct and interpret a 99% confidence interval. So that right there tells us that we're doing a 4-step process, right? So we want to do an interval of the difference in the means in the number of chocolate chip cookies for Chips Ahoy and Great Value cookies. All right, so the first thing we want to do is the state. And in this state, we want to estimate. We want to say what it is we're estimating. And so we want to establish which thing is getting subtracted from which thing, right? Does that make sense? So we want to say like Chips Ahoy, the mean Chips Ahoy cookie minus the mean Great Value number of chocolate chips in each cookie. So we want to sort of set that up and in the state, and then we got to use that same process, that same difference all through the problem. Otherwise, if we switch it around, then we're going to get the sort of the flip of the confidence interval. And so we need to be consistent. So make sure that you're setting that up, saying, what the difference is and what the different means are, and then also what confidence level. So pause the video and write that out. All right, so the state. So for me, I set up the mean subscript CA, standing for Chips Ahoy, and mean minus mean subscript GV, which is Great Value. And so I've set it up where it's Chips Ahoy minus Great Value. All right, so we want to estimate mu sub CA minus mu sub GV at a 99% confidence level. And now I need to say what my mu sub CA and mu sub GV stands for. So mu sub CA is the true population mean number of chocolate chips in those cookies. And mu sub GV is the true or mean population, true population mean number of chocolate chips in Great Value cookies. All right, so saying what you're estimating, say what confidence level, and then also make sure that you're explaining what symbol you use. And you have to set up which way you're subtracting the data. All right, let's go on to the plan. So state your inference procedure and check your 3 conditions. Again, pause the video and write that out. All right, so the plan is we're going to do a 2-sample T interval for difference in mu's. And again, you can write out actually that same mu sub CA minus mu sub GV so that we're consistent. All right, and we want to check conditions. So we randomly sampled 2 independent random samples. We can assume there's more than 100 of each type of chip, chocolate chip cookie. And then we sampled less than, we did 10 cookies of each, so that's obviously less than 30. Central limit theorem does not tell us that our sampling distribution of the difference in X bars is approximately normal, so we need to graph each set of data, and so I've done that here in my calculator. Again, we have them in list 1 and list 2, so we'll turn on 2 different plots. Make them both box plots. Use list 1 for one, list 2 for the other, and you'll see that neither one has an outlier, and neither one has any kind of strong skewness to it. So it's safe to proceed with our T procedures. All right. So here in the do, again, I'm going to show you how you could do it by hand, but I'm going to suggest that you don't do it by hand, that you use our 2 sample T int as our test. It's just less accident prone. You're just going to, all you really need to do is interpret the results. You don't have to be responsible for calculating all of the confidence intervals by hand. So run that now, pause the video, run all that on your calculator, and write out your results. All right, so again, if you're doing it by hand, you would have to go get your critical T value from either inverse T or from your T table. We have also would have to run some 1-var stats on our lists of data to get our X bars and our S's for each of the sets of data, and then plug them into the formula. But again, I would suggest that you do this instead, right? So you say, I'm going to use my TI-84. I'm using a 2 sample T int. I'm going to use the data. It's in list 1 and list 2. And so just be careful. You want to make sure, not a bad idea to kind of get your X bar and your X bar for both of them to make sure that this is in the correct direction, right? That your list 1 and your list 2, that you're subtracting them correctly, all right? Because if you don't, you'll get these same numbers, but in reverse. So you'll get negative 2.81 to positive 4.81. So you just got to be careful of how you're subtracting. How you set this all up is going to affect which direction your confidence interval is calculated in. All right, and now your conclusion. Again, pause the video and write that out. The 3 components in your conclusion. All right, so we are 99% confident that the interval from negative 4.81 to 2.81 captures the true difference. And again, I sort of emphasize it's Chips Ahoy minus good values. The difference in the mean number of chocolate chips in the 2 types of cookies. Okay. And then your final question, part to this question is part B. Does your interval provide convincing evidence that there is a difference in the mean number of chocolate chips? All right, and so we could think, we're going to do a hypothesis test in the next lesson, but for now, all we have to do is look at is the critical value that we're looking at, or the sort of hypothesized value, is it in our confidence interval? And so if there is no difference in the true mean, true mu, then we would expect 0 to be in our confidence interval, right? So if there is no difference, mu sub CA minus mu sub GV should be equal to 0. And we'll see that in the next lesson when we do a hypothesis test. But for now, we just look and say, oh, okay, 0 would mean there is no difference. 0 is in the range of plausible values because it is contained in our confidence interval. So this would show us, yes, we have we have evidence that there is no difference, or we do not have evidence that there is a difference. Okay, so your homework, you have 3 problems for homework, and those 3 problems each require 4 steps. So make sure that you're doing all 3 of these using your 4-step process. And this is due next class.